So Boyle's law states that a pressure of a given mass of an ideal gas is inversely proportional to its volume at a constant temperature. Boyle's law, or Boyle's equation, is P1 times V1 equals P2 times V2. We have a problem here saying a ball with a volume of 1.59 liters is filled with a gas at 7 atmospheres. If the pressure is reduced to 4.7 atmospheres without a change in temperature, what would be the volume of the ball? So we have that P1 is given, which is 7 atm, and V1 is given at 1.59 liters. P2 is given at 4.7 atm, and we need to find out the volume, the final volume. So right here, we just plug in the numbers. 7 for the P1, 1.59 L for V1, and then P2, 4.7. And then we just divide it so we can have V2 by itself, and we get that 2.37 liters is the final volume. Next we have Charles's law, which states that the volume of an ideal gas at constant pressure is directly proportional to the absolute pressure, or absolute temperature. We have here the equation V1 divided by T1 equals V2 divided by T2. And right here the problem asks a 750 milliliter sample of hydrogen is heated from 22 to 81 degrees Fahrenheit at a constant pressure. What is the final volume? So in order to work any of the equations out for any laws that were given in chemistry, we have to convert degrees Fahrenheit to Kelvin. So that's going to be the first step here, is turn 22 degrees Fahrenheit and 81 degrees Fahrenheit to Kelvin. In order to do that, we would have to, for 22, we would have to subtract, we would have to put 22 on top, subtracting 32 divided by 1.8 plus the 273.15, and that's exactly what we did here as well. We put 18 degrees Fahrenheit minus 32 over 1.8 plus 273.15, and then we get here that 300.38 is Kelvin for 81 degrees Fahrenheit, sorry. And then right here we get that 267.59 is the Kelvin for 22 degrees Fahrenheit. Then after that we plug it in right here. So this is what we have here. We have V2 equals 750 milliliters times 300.38 Kelvin divided by 267.59, and then we simplify all of those to get V2 equal to 841.9 milliliters, and we use that exact same equation. Next we have Avogadro's law, which states that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. So it can be different in different ways. Right here I have 3 different ways it can be written. V2 over N2 equals K, or V1 over N1 equals V2 over N2, or V1 divided by N1 equals V2 divided by N2. Right here in the problem, it asks a 7-liter sample of 27 degrees Celsius and 3 atm of pressure contains 1.5 moles of gas. If an additional 0.75 mole of gas at the same pressure and temperature are added, what is the total volume of the gas? So we are given V1, which is 7 liters, N1, which is 1.5 moles, and 2 is 2.25 moles, and we need to find out V2, which is the final volume. Then so I used the second or the last equation, but I switched it around because we need to find V2. So we put 7 for ATM, 2.25, which is moles in the final in the at the end, and then we have 1.5, which is the moles, the initial N, and we get that 10.5 liters is V. So Gay-Lussac's law states that for a given mass and constant volume of an ideal gas, the pressure exerted on the sides of its container is directly proportional to its absolute temperature. The equation can be stated like this: P1 divided by T1 equals P2 divided by T2. And the problem says a 25-liter cone contains 5 atm, which is atmospheres, of gas at 31 degrees Celsius. What would the pressure of the gas be if the gas was heated to 67 degrees Celsius? So first, we need to remember that we always have to put the degrees Celsius or degrees Fahrenheit into Kelvin. And whenever we go from degrees Celsius to Kelvin, we just have to add 273. And so we get that 31 degrees Celsius is equal to 304 Kelvin. And 67 degrees Celsius is the same as 34 Kelvin. And we just plug in the numbers right there. So we have 5 for the ATM, 340 for the initial temperature, and then divided by 304, which is the final temperature. And we get that it increases by 6 atm. The ideal gas law is a law describing the relationship of measurable properties of ideal gas. The equation for this is PV equals nRT, which P is for pressure, V for volume, N for number of moles, and R the gas constant, and T the temperature in Kelvin. So we have a problem here. It says 9.1 liters of an ideal gas is contained at 5 atm and 49 degrees Celsius. How many moles of this gas are presented? So we need to remember to put temperature into Kelvin by adding 273, which would equal to 322 K. And then we just plug it in. And right here, so 0.08 is the universal gas constant, so it always will be there in that problem. So R is the gas constant, which is 0.08, and we simplify it in order to get 17.67 moles. So next up is Graham's law, which says that the rate of effusion of gas is inversely proportional to the square root of the mass of its particles. So the equation is right here: Rx parentheses mmx to the power of half equals Ry parentheses mmy to the power of a half. So right here we have gas X has a molar mass of 78 grams per mole, and gas Y has a molar mass of 10 grams per mole. How much faster / slower does gas Y effuse from a small opening than gas X at the same temperature? So right here we have the formula, and then we just plug in the numbers. So 78 grams per mole plugged into X, and then to the Y is 10 grams per mole. We simplify that first because everything that's in the parentheses goes first, and then everything in the brackets. So we have 7.8 parentheses brackets to the power of a half, and right here we get that the answer is 3.9. So gas Y will effuse 3.9 times faster than the heavier gas X. Last but not least, but we will be talking about Dalton's law, which says that in a mixture of non-reacting gases, the total pressure exerted is equal to the sum of the partial pressures of the individual gas. So Dalton's equation would be expressed like this. So the total is equal to P1 plus P2 plus P3 and so on, and just represents like that it can be any number. The equation here says the pressure of a mixture of sodium, carbon dioxide, and nitrogen is 195 kPa. What is the partial pressure of carbon dioxide if the partial pressures of sodium and nitrogen are 35 kPa and 80 kPa? So we have 35 and 80 given, and we need to figure out what carbon dioxide is. So we add 35 and 80, and then we divide that by, or divide 195 by the total we get, and we get that carbon dioxide ends up being 80 kPa.